I'm Dr. Ron Eaglin, and this is COP 3530, Data Structures, and today we're going to talk about Big O notation. Well, actually, we're going to talk about a little bit more than Big O notation, because when you talk about Big O notation, which is really what you're going to hear if you're in computer science, is the concept of the Big O notation, we're talking about algorithmic complexity and asymptotic notation. And those are some big words. Algorithmic complexity. How complex? And what we mean by complex is we're not talking about how many lines of code. We're talking about mathematical complexity. How long, how much resources is it going to take to execute an algorithm? And when we talk about asymptotic notation, well, asymptotes are those things that go off into the sky. Is your algorithm going to blow up when you run it with large numbers, or is it going to remain stable and work? So we need to understand the concepts of both algorithmic complexity, algorithmic analysis, and asymptotic notation. Now, in the reality, you're probably going to be dealing mostly with Big O notation, which is the one that most people use to say, because Big O notation tells you pretty much everything you need to know in one simple little package about the complexity of an algorithm. It's not the only type of complexity that's out there. We're mathematicians and computer scientists and IT professionals. We love all the different ways of representing things, but we're going to look at just very scratch over the surface some of the other algorithmic analysis, some of the notations that are used. So, analyzing algorithms. And analyzing algorithms is literally just that. You sit down with an algorithm, a set of code, or a mathematical equation, and you work through how hard is this to do the calculations, how many operations are necessary to do this, and it can be complex, it can be quite challenging. Some of the hardest questions that you're going to be able to say, look at this algorithm and tell me what the big O of it is. But the bottom line is, when we say big O in algorithmic complexity, we're saying, if you're dealing with one case, or one of something, it might execute beautifully. Two, still fine. What's going to happen when you throw in 1 million records that need to be analyzed? Or, okay, is it going to still be doable? Or is it going to be so complex that it's going to take forever to actually do the computations? Scalability and time to complete operations. And that's what Big O is all about. When you look at asymptotic notation, well, it's the size of things increases. They usually approach a specific value. I've shown you here 3 asymptotes that are basically going to a line and they never cross it. That's not always the case. Suppose I threw in a sine wave into my vertical asymptote. It could go back and forth and back and forth and back and forth across that line. But as long as it's getting closer to that line, as you get to larger values of what we call n, okay, that is the asymptote, something that the function approaches. So let's look at a very simple example, O of n. You should all be familiar with for loops. For I equals 0 to I is less than n, I plus plus, do something, just something simple. Okay, nothing that causes any level of complexity, simple, straightforward operations, and this is O of n. As you increase n, it takes that many more operations. It's linear. Very straightforward. Quadratic, you can get a little bit more complex with quadratic, and quadratic is pretty simple to do. You've got one loop inside of another loop, so you've now got O of n squared. Again, an O of n squared is bigger than O of n. So anything that fits within O of n squared actually fits within, anything that fits within O of n actually fits within O of n squared, because your case scenario is out, you're on the outer upper bound. The rules of Big O notation, and I'm going to read these off to you. If f of x is a sum of several terms, you got many, O, so your function has an O of n, something is O of n, and O of n squared, and O of 2 of n. If there is one with the largest growth rate, the one that has the biggest O of n, and you need to know what has a bigger O of n. O of n squared is bigger than O of n. O of n is bigger than O of log of n. Okay, O of n log n fits between O of n and O of n squared. You need to understand that mathematics to know where they fit in order with each other. But in final big O notation rules, the biggest one. So if I took O of n and plus O of n squared and added them, the final value is simply O of n squared. Okay, in other words, you can just drop off. So you can omit the other ones. And constants don't matter. So x times something O of n is still just O of n, because x is a constant. We don't care about the constants. Why is all this? I mean, why do we not care about this? Because all we care about is making the determination of what's going to happen when n gets big. And those constants don't matter. And the terms that are less than the largest O of n don't matter. It's the big one that's going to control it. And here's a good example of this. Something that's O of n and something that's O of 2 of n. Well, when you're, and this is a good case because I'm saying, okay, every time you do an operation, every time you do something an n, there's 100 operations in the O of n case. So you've got a constant, 100 times O of n. And the O of 2 of n, there's one operation per n. There could be multiple, but we don't care. Now, in the n equals 1, n equals 2, n equals 5 cases, the O of n case has more operations being performed. Okay? The O of 2 of n does not. But we don't care about the small cases. We care about the asymptote. What happens when you get really big? So now you get down to n equals 20, and you're only up to 2,000 operations, but you go into the O of 2 of n, and you get to n equals 20, and you're up above 1,000,000 operations, which is a lot more than 2,000. So you can see that the O of 2 of n can blow up on you very fast. That's a simple power operation. Okay. And that's just one good example. The factorial example, other examples, you might have done the Tower of Hanoi O of n, and it blows up real fast. So that is the bottom line. You need to know what's going to happen. And what actually happens when you run an algorithm that may be O of 2 of n, and you put a number that's too large in there, the computer can literally freeze. You don't know what's going on. And that's why we don't care about those other things, those constants. We're looking for the highest order asymptotic value. Some common big O's: constant, linear, logarithmic, quadratic, log linear, factorial, and exponential. And some examples of things that actually have those common big O's. I did not, unfortunately, put them in the order. See, n log, well, it's close. I mean, log n goes before O of n. O of 1 is just, hey, however many you got, and there's no, n isn't even a value that's important there. But you will need to look at, and when you calculate O of n's, if you need to know for sure, just simply look it up. Some of these you're going to know right off the bat. I mean, O of log n, O of n is bigger than O of log n. Okay, O of n log n is between O of n and O of n squared. Okay, that should be pretty obvious to most people that are looking at this. It's just simple mathematics. There's other notations. And we're not going to spend a tremendous amount of time making sure that you can actually do and calculate and understand all the other notations. You do need to know big O. But you also should be at least a little bit familiar with, if I say, what's T of n, okay, what is that? Well, you know that's another notation, you know that it's an asymptotic notation, and that it actually is measuring something different from what the big O notation is doing. So when we're talking about T of n, we're looking at the maximum amount of time a function takes to run on any input size n. And what you do in T of n, well, you don't get rid of the smaller terms, you actually now care about those smaller terms. They're important. So that is kind of giving you a complete maximum case scenario. O of n is only concerned with the asymptote. Okay? And what I mean by that is you may have calculations that go above and below and above and below and above and below the asymptote, but you don't care about whether it's just slightly above or below. You only care about the asymptote itself. T of n, you do care. You actually care about those other little terms there. here is an interesting example about how that big O and the T of n are actually used. When we talk about T of n, we're talking about a maximum case scenario. So in other words, T of n has to be higher than the actual situation that occurs. Okay? That's an important factor of about T of n, whereas big O, the number of operations can go above your big O and go below your big O as long as it's approaching the asymptote. So you end up with some technical terms which are actually true. As long as I pick a T of n that's bigger than the actual T of n that's the closest T of n, I'm technically true. Not necessarily the most accurate, but technically not false, because of the way it actually says those equations. When I say T of n is equal to O of n 1000, I'm saying that T of n grows asymptotically no faster than n to the 100th power. Well, if you're in a situation where you do need to use T of n, and you can calculate T of n very relatively straightforward, just like you would O of n, okay, then you're really getting into a higher level of accuracy of what you need to be able to do for your algorithmic complexity. Whereas O of n is still going to be the important one because, again, you're looking to see, is this algorithm going to have issues? Okay. Little o. Little o is an interesting one also because the mathematical definition of little o is kind of interesting. So we actually read it just like we read big O. So big O, we'd say this is big O of n. Okay, we can actually say the same thing, saying it's little o of this. So if I say f of x is O of g of x, then f of x is little o of g of x is how you read it. And what it actually is telling you is that g of x grows faster than f of x. G of x is a upper bound. Now, if you're looking at the mathematics of this, and this is kind of an interesting way to look at the mathematics of this, I say that f of x is less than k of g of x. And what I'm saying when I say that is that for every value of k greater than 0, so notice k's got to be a number that's bigger because we're both going bigger, there is a constant, a, where this is true whenever x is greater than a. So in other words, I'm saying at some point above a certain value, the little o is always bigger than the value of the number of operations. It's always bigger. Now remember, little o, big O, you could have it still infinitely crossing over the asymptote. But little o, that asymptote, is an absolute upper bound above a certain value. Okay? May seem kind of hard to grab it, but I'm just saying at low values of n, or x in this case, it can go back and forth, but eventually you're going to reach a point where the little o is always going to be bigger than the actual number of operations. So how can I look at this? I can say big O grows no faster than. Okay, big O is an inclusive upper bound. How would I say it? Little o, okay, grows strictly slower than. And little o is a strict upper bound. Okay, inclusive upper bound means it's a bound, but it actually can go back and forth with it. Little o, it's always above it. Well, what are some other ones? There's omega, okay. Omega defines a lower bound. I'm not going to go into a lot of details about omega, but you've seen little o, so now you've got omega bound. And that's not just the last of the different notations because omega is looking at lower bounds, but we can also look at theta notation, and theta notation is where you're looking at actually the upper and the lower bound. So you're trying to define both sets of bounds. Again, recognition that these are same concepts as we have with big O, but different ways of looking at the problem. Strict upper bound, lower bound, both bounds, okay, exact numbers, all different ways of looking at the algorithmic complexity. So, hopefully, looking at this, and I hopefully have not created too much confusion, important, you know what algorithmic analysis is, that you can actually look at an algorithm and figure out, okay, what is the computational complexity of the algorithm? What does it look like when I put it in big O notation? Am I going to have problems with it blowing up? So I need to be able to determine big O notations for standard algorithms. I also need to recognize that big O is not the only algorithm, or not the only notation that is used to indicate algorithmic complexity and asymptotic is an asymptotic notation. There are other ones, and some of the ones that we looked at, T of n, little o, omega, and theta. Thank you very much. I hope I didn't confuse you too much, but hopefully you can definitely figure out the big O notation of those algorithms, because that's what we're going to be doing. Signing off from Daytona State College.